Here we'll continue on the power flow problem with the same 3-bus example we have discussed for the admittance bus matrix. Now let's say that we have a 3-bus system shown here, and now we also say that every line is having the shunt susceptance of J0.02 and the series impedance of the line is J0.1. And now we need to solve the power flow problem, and we need to understand that in this power flow problem, the bus here is connected to a generator and it is given as a slack bus or a reference bus, and this is also a generator bus, but it's considered as a PV bus, and is a load bus where we take it as a PQ bus, and the respective values are also given in the problem itself. That is, for this reference bus we know what is the voltage and angle, that is considered as 1 at an angle of 0, and for the PV bus we have a voltage value given as 1.05 and the generator power output as 0.06661, and then the load values are also available for us in the problem itself. Now, while solving the load flow problem, for the first thing that we need to know is the admittance bus matrix. Now, we've seen that given the line susceptance and also the series impedance of the line, how do we calculate the bus admittance matrix of a given network? We have calculated that, and for this particular problem, we know that the admittance bus matrix is this one. Now the next is, after you know what is the admittance bus matrix, you first need to know, okay, how many buses are available in the system, and what are the generator buses or PV buses, what are the low PQ buses, and where is the slack bus, and then we need to consolidate what values of the voltages and angles we already know and what values of the voltages and angles that we don't know. In order to do that, let's have the summary of the system data that we have here. The first bus that we have here is the reference bus. Now if it is a reference bus or a slack bus, or we even can say it as a swing bus, is where you consider that the voltage and angle values are available to you. That means that the real and reactive power are the unknown quantities. That is for the bus number 1. Now for the second bus, that is actually a PV bus, is a generator, where we have the real power quantity and the voltage values are mentioned, but we do not know the value of the reactive power output and angles. That is our second bus. And now the third bus is what is the PQ bus, load bus, where you know the values of real reactive power loads, but you don't know the values of the voltages and angles. Now, this is what is the way you need to figure out, first of all, in the given system, where is your reference bus or a slack bus. And then, what are the PV buses? And in case of all PV buses, this is what is the general thing where you know the values of the real power and voltage, but you do not know the values of the reactive power and angle. And now you need to know what are the PQ buses in the system. So now here we have only one PQ bus, so even if there are multiple number of PQ buses, at every PQ bus you know the value of real and reactive power load, but you do not know the values of the voltages and angles. Once you summarize, the second step in the power flow problem is you knowing the values of the unknown voltages and angles. Now you can look at the list of unknown variables, and angles that you don't know are theta 2 and theta 3. In a way, you know only angle at the slack bus, but you do not know the angles at all other buses. And now the unknown angles are theta 2 and theta 3. We have mentioned it there. And the unknown voltages, if you see, you do not know voltage only at bus number 3. That is V3. That's the second step that we have. The third thing is, in order to solve a problem using Newton-Raphson method, that's where we wanted to know what are the real and reactive power quantities that we know of. So now we can get into the known power variables list and figure out what are the real and reactive powers that we already know. You can see that the values of P2 and P3 are already available for us, and then Q3. So now these are the known quantities that we use as the functions, and then try to minimize the difference between the calculated values of the powers and then the specified values of the powers. So that's what is the third statement or the third thing to be figured out in the power flow problem formulation. Now once you have that, so what you have is, okay, what are the three real or reactive powers that we already know, and then what are the unknown quantities that we have in our system, and what is the admittance bus matrix. After you have it, another important thing for us is, okay, fine, let's have a look at what is the Jacobian matrix. As we are not discussing the fundamentals of the Newton-Raphson method here, we are just trying to solve the problem. So we can just say that for the unknown functions, three functions that we have defined, that is three powers, the unknown values are nothing but the values of theta 2, theta 3 and V3. Then the Jacobian matrix is going to be the partial differentiation of that P2 with respect to, that is the known value of P2 with respect to all the unknown quantities, partial differentiation of known value of P3 with respect to all unknown quantities, partial differentiation of known reactive power quantity with respect to all unknown quantities. That's what is our Jacobian. Now, in the case of iterative process, we need to know the functions that we have in this Jacobian matrix. In order to get that, first we need to have an expression for P2, P3 and also Q3. We need to know the expression for the values of P2, P3 and Q3. These are nothing but the expression for the known quantities of real and reactive power. In order to do that, if you look at the expression for the real power injection difference at a bus, that is, first we write down what is the real power expression and then what is the actual value of the real power that is injected at that bus. So the difference is nothing but delta P. So delta P at a bus is expressed this way. Now if you try to substitute the values for the 3-bus network that we have, that is delta P2 and delta P3, we can calculate by expanding this particular delta Pk for a 3-bus network. So now once you have that, I also highlighted the unknown values of the angles and voltages in these equations. So we have delta P2 equation, delta P3 equation. One thing that you need to observe is that power injection is actually the generation minus load. At this P2, we have generation, but we don't have a load. So that is like PG is available, but PL is 0. So that's why you have a negative number here. But in the third bus, we have load there. That means the load is available, but generation is 0. That's a negative quantity for us. So negative of negative will be positive. That's where you have in the delta P3, the value of the real power is positive here. Whereas the other terms can be expanded. Similarly, we also have an expression for the reactive power difference injection. So that is delta QK. Now, if you have, this is what is the QK, and whereas this is the actual value of QK, the difference is what is delta QK. And now again, Q3 is what we are calculating here. We have only load, we don't have any generation. That's where you get that number to be positive for us. So we have delta Q3 expression. At the end, you have an expression for delta P2, delta P3 and delta Q3. So these are the three known real and reactive power quantities for us. So once you have an expression for the delta P2, delta P3 and delta Q3, this is what is to be used in order to get the elements of your Jacobian matrix. What is Jacobian matrix? Then the partial differentiation of that P2 with respect to theta 2, theta 3 and V3. Similarly, partial differentiation of P3 with respect to theta 2, theta 3 and V3. You can see that the variables are already available in the respective functions. Now, we'll start with the calculation of elements in the first row of this Jacobian matrix. So if you try to calculate the elements in the first row of the Jacobian matrix, that is the partial differentiation of P2 with respect to theta 2, theta 3 and V3. So that's where we have an expression for delta P2. That differentiation with respect to theta 2 can be calculated. That is, when you differentiate it with respect to theta 2, the sign is going to be cos, and then you also have sine theta 2 here, so that also will become cos here, and that constant differentiation with respect to theta 2 will be 0. Similarly, delta P2 differentiation with respect to theta 3, the first term doesn't have theta 3, so that will become 0, and the sign of that theta 3 is available, so that becomes cos, and again you need to differentiate that minus theta 3, that's where you will get this negative here, and the constant term will be 0. And the third thing is where you are differentiating that delta P2 with respect to your V3. So now when you differentiate it with respect to V3, first term doesn't have V3, so the second term is having the V3 as the coefficient, so the rest of the part will be your partial differentiation there. So this is how we'll be getting the elements of the first row in the Jacobian matrix. So this is actually the expression for each and every element in the first row of the Jacobian matrix. And similar to that, if you wanted to get the elements in your second row of your Jacobian matrix, then in order to get that, we have an expression for delta P3, then find the partial differentiation of delta P3 with respect to theta 2, theta 3, and V3. So that's a very similar exercise, the way we have calculated the differentiation for P2. And then we also have an expression for Q3. Then the third row can be calculated by differentiating that Q3 with respect to theta 2, theta 3, and V3. So that's where after calculating the partial differentiation of all these functions with respect to the unknown values, that's where you will get your total Jacobian matrix to be somewhat similar to this. So this is what is our Jacobian matrix. Now, let's start the iterative process, because what are the steps involved in finding the solution? First thing, we have what are the unknown variables. Then we will have initial guess, and we'll use that initial guess and calculate what are the values of those functions. So we expect those functions to be 0. This is, let's say you have 3 functions here. We expect these 3 function numbers to be values to be 0, provided the solution that we have considered is the right solution. So we'll calculate the values of these functions, that is nothing but delta P2, delta P3, and delta V3 here. So expression for calculating all the 3 powers deviations is available for us. So once you have that, then if that delta P2, P3, and Q3 is not very close to 0, that's when you will go for the continuation of that iteration, where the third step is find what is your Jacobian matrix. So we have an expression for the Jacobian matrix, then we'll substitute our initial guess in these particular equations, then we'll get what is our Jacobian. So now you have Jacobian matrix, you have your function values, you have your initial guess, that's what is used to update your values. How do you update? What will be the update? That is delta x is nothing but negative Jacobian inverse. Negative Jacobian inverse, that's where you calculated your Jacobian matrix, multiplied by the function vector. So function vector is in your step 2. So Jacobian inverse multiplied by the function vector, negative of that is delta x, and then you will have your first update value of x, that is x1 is x0 minus j inverse of f of x0. Now we will again use that x1 as the starting point and go through these steps and keep updating the values of your unknown quantities until you get your function values to be very close to 0 or less than your tolerance value that you have considered. Now let's follow the same process here. So I actually have the similar steps that you start with an initial guess, then you will calculate your function values, that is delta P2, P3, and Q3, then you will calculate your Jacobian, use the Jacobian and function values to get the update required and update your number. So the first step for us is to have an initial guess. So most of the times we'll start with a flat voltage profile. So the flat voltage profile for us is assuming that the angles are 0 and voltages are 1 per unit. So that is our initial guess. Any unknown angle is considered as 0, unknown voltage is considered as 1. So substitute these values of the unknown quantities in the expression of your functions. That is delta P2, P3, and Q3. We have already expressions for all these 3 functions. Calculate that, and then you will get what is f of x0. Then substitute the same initial guess in your Jacobian matrix. We already have an expression for the Jacobian matrix. Substitute those numbers there, then you will be getting what is your Jacobian matrix value. So after you have that, you can update your solution as x1 is nothing but solution after the first iteration is x0 minus Jacobian inverse multiplied by f of x0. So x0 we have, that is 0, 0, 1, and then Jacobian inverse, we have Jacobian matrix, we can find the inverse of that. And then you have your function values, use that and get what is your updated value of x. Now remember, when you have your solution, then the delta x will have its angles in terms of radians. And usually we always tend to consider the solution in terms of degrees. So be careful that the solution that you have is in terms of radians. So that has to be converted into degrees first, and then you can find what is your solution after the first iteration. Now once you have your first iteration, then you can see if that solution is enough or not. If not, then go for the second iteration. So now in the second iteration, whatever the solution we had in the first case is the starting point. Then use that x1, we call that as x1, use that x1 and calculate what are the values of your function. And use that initial guess and calculate what are the values of your Jacobian matrix. After you have your function Jacobian matrix, then use that to update your solution, where your x2 is x1 minus Jacobian inverse multiplied by f of x0. That's where you will get your x2. After you have your solution x2, what you can do is calculate what is the value of f of x2. So if f of x2 is close to 0, that's where you have a 0.00190023. If you're happy with the tolerance, then you can stop your iterative process. Otherwise, you can go for one more iteration to get the delta p and delta q values to be much, much lesser. But this is the repetitive process that we follow in order to solve the solution of the power flow problem we have here.